Okay, so we'll start off discussing stellar formation and evolution. And that's the subject of chapter 14 from your textbook. So the question is, how do stars form and where do they form, right? So to get some kind of meaningful answer, what we need to do is we need to look at the neighborhood of youngest stars, right? Because then we can get some hint as to how the stars are formed and where. Right? To find out something about the formative years of the child, you go to the kindergarten, right? And observe and are able to make some conclusions. Okay, so how do we know which are the young stars? Well, you need to recall so-called Hertzsprung-Russell or HR diagram. Those of you who took Astronomy 1P01 will recall this so-called HR diagram, where we, for a group of stars, say in a star cluster or several clusters of stars, we measure for each one of them its luminosity, which is the energy output of a star, and the surface temperature. And for historical reasons, the temperature is taken to increase from right to left this way. Okay? So when you do that for a large number of stars, you realize that they break up into three distinct groups. This diagonal group here is so-called main sequence, and over 90% of all stars belong to this group. Then, so you see in the main sequence group, we have stars at the upper left corner, which are extremely luminous and also very hot. Okay? And as you move down, the luminosity, the energy output drops, and also the temperature drops. So at the upper left corner, we have very hot and very luminous stars. And in the right, lower right corner, we have cool, dim stars. There are two additional groups. I'll just comment on them for the sake of completeness. Here are so-called white dwarfs. They are remnants of medium stars, medium mass stars like our sun. And here we have so-called red giants. So basically they are stars in final stages of their life when essentially all of the fuel has been used. Sometimes we refer to the temperature as spectral class, as those of you who took Astronomy 1P01 will recall. Starting from the highest temperatures to the lowest one, we have spectral classes O, B, A, F, G, K, and M, right? So the hottest stars are O and B spectral class, and the coolest ones are M. So there is one important relation for main sequence stars between their mass and their luminosity that help us estimate their lifetime. First of all, it's proportional to the fuel that the star has that is available to it to convert it into energy. And the fuel that is available is given by the mass of the star, M, and is inversely proportional to the energy output. For a given amount of fuel, the higher the rate at which the energy is burned, the shorter the lifetime is going to be. And basically, the energy output is the star's luminosity. Okay, so the lifetime is basically given by the ratio of the mass of the star over its luminosity. But now, Arthur Eddington found out that for main sequence stars, and only for main sequence stars, that the luminosity is proportional to the mass of the star raised to the power 3.5. So then the lifetime of a star is given by the ratio of its mass, and I can replace the luminosity by mass to the power 3.5, and I get that the lifetime of a star varies as 1 over mass raised to the power 2.5. So what you need to remember is that this implies that the larger the mass of the star, the larger the number in the denominator, and therefore when I more than square it, I square it and multiply by the root of it, the lower the ratio is going to be. So the larger the mass of the star, the shorter the lifetime. Okay, so then, because the mass and the luminosity go together with the main sequence stars, we know that those that are very luminous, those at the upper left corner of the main sequence, are going to live the shortest period of time. So they must be the youngest stars, right? Because if they are around, if we can see them, that means that they've been formed not that long ago compared to, say, our sun that was formed as a star about 4.5, 4.6 billion years ago. So when we look at these stars through a telescope, we always find that they are surrounded by clouds of gas and dust. And the composition by mass of the gas is that 75% roughly is hydrogen. Chemical symbol for hydrogen is H, and 25% is helium, the second lightest element, and dust. Okay, so here is the photograph of a very hot, probably a B-type star, big spectral class star, surrounded by the clouds of gas and dust. Okay? So whenever you look at one of these youngest, very luminous and very hot stars, you find out that they are surrounded by the clouds of gas and dust. So that has to do something with the formation of the star. When we can observe these clouds of gas and dust at visual wavelengths from 400 nanometers to 700 nanometers, we call them nebula. So from 500 nanometers to about 700 nanometers, that's the part of the spectrum of visible light. By the way, 1 nanometer is 10 to the minus 9 meters. Okay? So when that is possible, we call them nebula. And there are 3 major groups of nebulae. This is just one example. This particular kind is known as a reflection nebula. And it tends to be bluish in color. Okay?